Hi, it's Terry Denery of the MathWorks. So we're going to do another homework problem. It's going to be a statics problem, mechanical statics, and it's a real interesting one. All right, and so it's basically this sine frame. It's got essentially this kind of hinge connection, and the whole thing's supported because you got this cable here. So the cable essentially supports the load, so it basically doesn't move. All right, so let's see. So I did a little bit of, I'd say, annotation on this, and I just kind of added appropriate vectors, and this is what I will copy and put into our live script. And so that's kind of big, so let's just go in here, and let's just reduce this so it fits a little nicer. That's good. Okay, so couple of things on this, right? So the real driver of all the loading really is going to be the sine itself, which weighs or which has a mass of 20 kilograms, and then the beam itself has a mass of 10 kilograms, right? And it is a statics problem, meaning acceleration, whether rotational or angular, or straight line or translational, that's equal to 0. And so basically from F equals ma, we get these really important equations that we do in statics, which is sum of forces in both x and y, so that'll be two equations, will be equal to 0, and then your third equation will be the sum of the moments is equal to 0, right? Now, the cable kind of presents something that I think is real interesting and it's real important. And I think almost always when I work on mechanics problems, I like to understand the x and y components, right? And so, you could look at these questions here and go, well, that's basically what all the blue arrows are, and that's kind of true. But these red arrows, I think, are really important to calculate too, right? And so these are essentially the x and y components. And it's this whole idea, I love kind of this way of looking at vectors, that the length in x is simply the projection in that direction. And for a given angle, which we know we're going to call theta, that'll be the cosine of theta times the magnitude of tension, and then we'll get the sine of theta to get the y component of it. So anyways, let's go ahead and get started on this. So we go in here and we get into code mode. And the first thing we will do is let's do these calculations of weight, right? And so to know weight, we need to know what gravity is. And so I'll put in 9.8. Put my glasses on, all right? All right, and then we need to know the masses, all right? And so m sine is equal to 20, and that'll be kilograms. And I always like to do things in metric because the units become way, way easier that way. All right, and so then let's see, m beam, I'll call the other one, is equal to 10. And let's do the weight calculations. And beam and we'll do our first calculation. So we got those numbers calculated now. All right, and here's an opinion. I think it's a pretty good opinion. I always like it when my algebra is easier. All right, and so we got the three equations I mentioned, and what I'm going to recommend is do the moments first, right? And I think that from what I recall from when I took all these classes in engineering school, that is sort of how we did it. And so even though it seems like this big hassle, exaggerating, at least this responsibility of choosing a reference point to do moments, you can choose those things very tactically, very conveniently to kind of make your math simpler, right? And so to me, it's kind of obvious this point where your reaction forces pass through it, as well as your x component of tension passes through it. Well, why do I like that? Well, any force that passes through your reference point, they will contribute 0 moments or 0 torques, if you like the word torque better. All right, and so that's going to be our reference point right here, right? And you can begin to get into the whole thing, which are, well, these lengths, it's R cross F. That's what the moments are. These R's, these lengths are important, all right? And so anyways, I'd say the length of the beam which will be the moment arm for ty. Okay, this 1.3, which is the moment arm for the sine, and then the center of the beam. Those will be our important lengths. All right, so let's put those in now too. And you can see right there the length of the beam is 2. Okay, now the action of the force will be half that. It will be at the center of mass, and so let's put that in 2. It's equal to L beam divided by 2. And then they tell us the third one, which is the location of the sine. So L sine is equal to 1.3. All right, so let's get into formulation. From sum of moments equal to 0, we're going to get essentially the moment associated with the sine, with the beam, and with the tension. Right. Tension is the only one that would drive rotation in the counterclockwise direction, which by our convention will be the positive one. Right. And so maybe I'll start with that one. Ty times the moment arm will be the full beam length, so L beam. And then the other two will be in the other direction, so we'll subtract those off. And so we'll get minus L, L sine times W sine minus LCM times WB. And all that's equal to 0. Right? And so we're going to use this, and say use specific variable names that we put into our MATLAB code. And so I think we'll get this pretty quickly. All right, and that the kind of the trick to this one is essentially isolating ty. Everything else is known, and so it means I'm going to take these two terms and I'm going to put them on the other side of the equal sign. So Control X. All right, and to do that, we're essentially subtracting those terms from both sides, and a subtraction of a subtraction will make these positive terms. All right, and we're pretty close to having this done now, and it's really just divide through by that beam length, and we can solve for y, or t sub y. All right, and so we're almost there to answering our first question, but again, what we just solved for is the y component. And so we know that that y component is the overall tension times the sine of theta. And so to get t, yeah, I think it's so important we even do this. So let's get back into talk like a person mode, and we will have Tx is equal to t times cosine, and I'll use my term. What was it again? Oh, I didn't put it in yet. All right, so let's get that in there too. Okay. I'm going to call it theta given. No, I'm not even going to mention theta. I'll say angle given. Is this one up here 60 degrees? But I really care about this, And what I'm going to do is essentially recognize, well, that's a right, 90-degree angle. Therefore, this is a right triangle. And it means that these two other angles, well, they need to sum up to 90 degrees. And so, but let's take the numbers as given. Oops, let's put the equal sign in there. All right, and let's solve for theta. Equals 90 minus angle given. All right, and let's get that in radians as well. Put that on my, what they call it, buffer. I'm going to copy it basically. Is equal to theta times pi divided by 180. All right, and so we have that for tx. And it'll be sine for ty. Okay. Oops. All right. And I give myself a little bit of text here, kind of a, well, basically explaining what I believe is super important, which is get your x comma y components of tension vector. All right. I think that's good enough. All right, and so now let's solve for t. And so take this equation, Control E, we'll paste that in. And I think you can see it. We got to divide both sides by sine theta rad. And so my little shortcut will be, I'll put the divide in here, and I'll just relabel this as ty. And that'll be t. And we'll hit run. And so 352.8 newtons. All right. So we just solved for the cable. Now we're going to get these x and y components, which I got these small blue arrows representing that. And so how do we do that? Well, we've already used sum of moments equal to 0. So I'd say let's go for the low-hanging fruit and do x first. And the reason I'm calling it that is, well, there's really, the reaction force in x, and there's the x component of tension right there. Right? And so so I'll say from sum of forces in x equal to 0, we get basically, I'll call it Rx, the reaction force, plus Tx is equal to 0, right? And we can see that Rx is going to be the positive one because that tension is kind of pulling the beam towards it. So we'll probably address a little bit of a sign issue as we get into this. So let's go Control E, and so we'll go Rx is equal to minus Tx. Now Tx has not been calculated yet, so if I were to run it right now, it would kind of tell me that. And so let's get Tx right here. All right. And what we see, is that it's supposed to be acting in that direction. Let's hit run again. And I'd just say that probably the appropriate correction on this is probably, again, looking at your picture, kind of seeing it's been defined in a negative x direction. Maybe do it this way. So put the minus sign in right there. And minus. And so that gives us Rx is positive 305. Right? And so we're almost done with this. And of course, the last piece of this is sum of forces in y direction equals 0. And before we get there, it's just going to write it out. And again, I want to go look at the figure, and we see reaction force y, tension force y, negative on weight of sine, and negative on weight of beam. All right, and oops, minus w sine minus w beam equals 0. And maybe the easiest way to do this is just get rid of that. Let's put that as an equal sign, and essentially everything that was on the left other than ry we subtracted from both sides, and so that's now minus ty, but the other two terms will be positive. All right, with that I think I got it. So anyways, thank you very much.